Good morning, everyone. My name is Jaydev Esram, and I'm doing my master's in data analytics and computational science at Digital University, Kerala. I'm here to present my recent research article titled Spatiotemporal Patterns in a 2D Lattice of Hindmarsh-Rose Neurons Induced by High Amplitude Pulses. This work was conducted under the supervision of Dr. Shishankar Muni and Dr. Igor Eshepale. Now, let's begin with the introduction. Neurons are the structural and functional building blocks of the nervous system. They communicate with other cells via synapses, where electrical signals trigger the release of neurotransmitters. This activates receptors on dendrites of postsynaptic neurons, which propagating the signal. Neurons exhibit nonlinear dynamic behavior, making them ideal subjects for mathematical modeling and simulation. To study neuronal dynamics, various mathematical models have been developed. There are two types mainly, continuous systems and discrete maps. I have given Fix-Hugh-Nagumo model and Cialvo neuron map as an example for continuous system and discrete maps, respectively. These models help us simulate and understand the complexities of neural interactions and behaviors. Neurons exhibit excitability near a bifurcation point, leading to complex spatiotemporal patterns. These patterns are often seen in excitable media, where interactions can produce phenomena like spiral and target wave. And these spiral and target waves are emerge as is a result of in the lattice network of neurons. And this is the simulation of Velesov-Shaponsky reaction, which is a chemical reaction. Here also we can see that there are spirals and target waves are forming. Are forming. And these spatiotemporal patterns play a critical role in understanding biological phenomena. For instance, experiments have shown that in cardiac tissues, spiral waves are associated with arrhythmias. And this offers insights into mechanisms that disrupt normal heart rhythms. Similarly, in neural networks, these patterns help decode synchronization and desynchronization process, which are relevant in diseases such as epilepsy. And Hindmarsh-Rose model is a foundational system for simulating neuronal activity. And it is characterized by a system of three ODEs as given in this equation, where X is the membrane potential, Y is a fast recovery variable, Z is a slow adaptation current, and other parameters governs the neural dynamics. And this model captures a range of behaviors like bursting, spiking, and chaotic dynamics. Here you can see examples of the model's phase portraits and activity patterns, which form the basis of our network simulation. Coming to methodology, we set up a 2D lattice of 50 cross 50 Hindmarsh-Rose neurons coupled non-locally, meaning each neuron interacts with a subset of its neighbors. And I have given the schematic representation of the non-local coupling for different locations of the selected nodes. The local coupling means the neurons are interconnected with the immediate neurons surrounding to the neuron under consideration. And we modify the HR neuron to a network equation like this, where we introduced the external impulse f of t, and non-local coupling is introduced in the first equation. And sigma is the coupling strength, p coupling range, and q total number of connections in both directions for each node. And the boundary condition is defined by this following equation. And the external force is described by the following equation, which is a sinusoidal, periodic, which is a periodic Gaussian pulse. and it represents a periodic time series of Gaussian pulses with an amplitude A, which periodically repeats in time with frequency omega. And we have solved the equation, solved the network equation by using the numerical integration method, RK4 method. Initially, in the absence of external influence, the network exhibits a spiral wave chimera. This pattern is characterized by coherent and incoherent dynamics coexisting in space. As you can see, this is the initial state of the autonomous system, where the center core of the spiral uh, is incoherent, and the other part, then the wavefront is actually coherent in nature. And the space-time plot of the cross-section through the coherence core shows that the core localization is stable in time and does not change in the spatial range. And the normalized spectral density reveals four key frequency governing this pattern. And these frequencies are important for our study. By varying the pulse parameters like amplitude and omega, we have constructed this regime map. The regime map depicts how the dynamics of Hindmarsh-Rose neuron network change under the influence of high amplitude Gaussian pulse. And the corresponding spectral density is also given. The dynamics are strongly influenced by how the pulse frequency aligns with the spectral peaks of the network's autonomous oscillation. When omega matches these peaks, distinct behaviors emerges, as shown in different colored regions of the map. And our focus is on strong external forces where the impulse amplitude exceeds the network's natural oscillation amplitude. And these are the spatiotemporal patterns emerges as a result of the numerical computation. And you can see that unstable spiral wave regime is the most extensive region in the map. And when the spectral when the omega matches with the main spectral peak of the autonomous system, uniform oscillations can be seen, and the width of the that regime is increasing with as the amplitude is increasing, and when omega is near the and omega is close to second or fourth, omega is close to second or spectral peaks, we can see the frozen structures where clusters of neurons form with fixed spatial localization. And these frozen structures maintain their spatial layout over time, even though the nodes within the clusters are continue oscillating. And another regime is incoherence, which is marked in violet region, where here the oscillations become disordered with significant phase difference even among neighboring nodes. The other two other regimes are labyrinth structures and labyrinth-like structures of spiral type, and double front spiral wave and multi-front spiral wave. These all are very rarely in the figures, and these all are forming when close to the close to the boundaries of other regimes. Now let's look at the dynamical regimes, each by each. The unstable spiral wave regime, it it actually represents the initial chimera pattern. Initial spiral wave chimera pattern loses its stability as soon as the pulse is influenced, and it becomes unstable, and spiral wave regime is appearing. And the wave centers shift over time, leading to constant variability in the network. As you can see, the snapshots of the regime for various instances, and the spiral waves and spiral wave chimeras are forming and destroying and forming again. And this regime is widespread, especially when the frequency omega is far from the spectral peak maxima of the and the amplitude is very low. And the network exhibits continuous changes in spatiotemporal patterns, making it most dynamic and unstable region on the map. And we get a noisy but similar in structure and normalized spectral density with a peak at a low frequency. Next, we have the uniform oscillation. Here, external pulses synchronize the oscillations across the network. Every node oscillates in unison with nearly identical instantaneous phases. This is a snapshot of the regime. And even though the nodes exhibit oscillation that are similar in phases, but they are not exactly identical. And this is evident from the spatial profile for the cross-section. For a particular cross-section. And for the spectral density, we can see that a lot of new harmonics appears in the power spectrum. And this synchronization creates a stable and uniform spatiotemporal profile, which could potentially utilized in neural networks, cardiac rhythms, where coordinated activities is important. Frozen structures occur when the pulse frequency aligns closely with the second or fourth spectral peaks of the autonomous network. And this is a snapshot of the regime. In this regime, the network forms stationary clusters where nodes within a cluster oscillate with similar phases. We can see there are two colors, the green and the red. So basically, they are the two clusters. And the nodes within the clusters are oscillating. So the term frozen does not mean there is the absence of oscillation. The nodes within the clusters are oscillating with their own phases. And these clusters remain fixed in space over time, while the nodes themselves continue to oscillate. And the space-time diagram reveals that it is a standing wave. And we got a smooth power spectrum with two additional harmonics between initial spectral maxima. The regime of frozen oscillation is typical for biological systems. For example, frozen structures in cardiac rhythms can manifest as sustained patterns of heart muscles contractions that persist unchanged over a specific time interval. The incoherence regime represents a chaotic response to external pulses. When the pulse amplitude is high and frequency deviates significantly from the spectral maxima, the network enters a state of disordered oscillations. Neighboring nodes display significant phase differences, creating a highly irregular and unpredictable spatiotemporal dynamic. And close to the boundaries of frozen structures and unstable spiral waves, we observe new regime called labyrinth-like structures. There are two types we are going to look into of the labyrinth-like structures. The first one is in the current slide, I will talk about the labyrinth-like structure of spiral type, and snapshots of two types of these are given. The only difference is the width of the strip actually. The first one is actually the narrow strip, which consists of 2 to 4 nodes, and the other one is which is more wider, approximately 4 to 8 nodes. 8 nodes, and despite the similarity with this spiral wave patterns, we do not observe any rotation of wavefronts here. And the difference, like I said, the difference lies in the strip width, and oscillators within the same strip exhibit similar phases, while those in adjacent strips often oscillate in antiphase. This can be understood from the time series of different nodes, and the standing wave becomes more complex, and the spatial shape of the standing wave becomes more complicated, as you can see here in the space-time plot. For the second type, where in the second case where the strips intersects vertically and horizontally, and it is very similar to the preceding one. Here also there are two typical cases. We explore the two typical cases. The first one is given here. And the spatial structure is stable, just like a frozen one. Here also, the spatial structure is stable, just like the spiral type. Here also, oscillators of one strip have similar instantaneous phases, while elements of adjacent strip oscillate almost in antiphase. This can also be can be understood from the time series. And the second one is actually unstable. The spatial profile is unstable for this particular labyrinth-like structure. And strips can be realigned when new intersections of horizontal and vertical strips occur and disappear. Next is the double front spiral wave, a particular intriguing regime. And unlike traditional spiral waves with a single wavefront, this regime features two closely spaced wavefront. As you can see, in previous we have seen a single wavefront. Here we can see the two wavefronts propagating. And this dual fronts contour is visualized in an immediate spatial cross-section across the wave center here in the spatial profile. And space-time plot for an extended period shows that the wavefronts move extremely slowly, with oscillations of individual nodes being independent of the wave dynamics. Lastly, we observe the multi-front spatial wave regime. Here, the wavefront behaves similarly, but it consists of several fronts, typically 3 to 5 nodes. And here also the wavefront slowly rotates around the wave center. But the only thing is the spatiotemporal structure is unstable in time. We can see that especially the inner side of the wave is getting destroyed and occurs again during the rotation. Despite this difference, the features are very similar to the double front spiral waves. The diversity of these regimes demonstrate the remarkable sensitivity of neuronal networks to external forces. In conclusion, periodic high amplitude Gaussian pulses induce both destructive and constructive effects on network dynamics. While some pulses destabilize initial patterns, others create unique spatiotemporal structures like uniform oscillations and labyrinth-like patterns. Emergence of novel multi-front waves near regime boundaries highlights the complex interplay between pulse amplitude and frequency. These findings pave the way for controlling neural network behaviors, offering insights into both natural and artificial systems. Thank you.